Well, hello, welcome again to our journey into complex analysis, and we're up to section 9, which is on Taylor series. So a power series is a series of the form sigma a n z to the n, which you can think of as a Taylor series about z equals 0. The Weierstrass M test that we mentioned in the previous section shows that if we have this sequence of complex numbers and this series converges for some r bigger than 0, then we can use Weierstrass M to show that this series converges uniformly inside this disk. For example, z to the n on n factorial converges uniformly for any r bigger than 0, since the sum r to the n over n factorial converges to e to the r. We say that a power series sigma a n converges absolutely if the sum of the moduli of the terms of the sequence converges. And we have this very useful idea of the radius of convergence. If we've got a power series here, there are examples of such theories that converge absolutely only at z equals 0. On the other hand, we've seen above an example of a series that converges absolutely for all z in C. So if a power series does not converge absolutely for all z, then there is a real number r for which the series converges absolutely inside this disk, mod z less than r, and does not converge absolutely outside of the disk. What's happening on the disk is another question. This real number r is called the radius of convergence of the power series, and if the series converges absolutely for all z in C, as with our series we mentioned above, this series up here, which is going to of course converge to e to the z, then we say the radius of convergence is infinite. Note that nothing's been said about what happens on the actual circle. There are various techniques for finding the value of r. So for example, if they exist, these two formulae here give you the radius of convergence. This is connected with the ratio test, and this is connected with the nth root test. So if these limits exist, then these will give you the radius of convergence. But there are examples, we'll see one in a moment, where neither of these two things exist, but there is still a radius of convergence, and we have a more general formula for calculating the radius of convergence that works in every case when the radius exists. So just to recall some notation, if we have a real sequence b sub n, we define Cn to be the supremum of bk for k bigger or equal to that fixed n for each n in the sequence. Then, if this Cn converges to some number c, then we write c as the lim sup of Bn. Now, one formula that works in every case is this formula for the radius of convergence, which is 1 over the lim sup of the nth root of the modulus of a sub n. This formula is sometimes known as the Cauchy-Adamard formula. And just to do a couple of worked examples here, using what we've had here. So, looking at this one here, for example, we're going to use the ratio test for the first one. So we are looking at the sum n over 2 to the n z to the n. So by the ratio test, we let an be n over 2 to the n, and we look at this limit of a sub n on a sub n plus 1. So we copy a sub n and then invert and multiply, and this comes out to be 2. So this is our radius of convergence r, and the series then converges inside of this disk centre of the origin radius 2. So that's just that ratio test version of it. To see an example of where we need the more general Cauchy-Adamard limit, we look at this series here of 3 plus minus 1 to the n all to the power of n z to the n. If you try the nth root test on this sequence, then it doesn't work. because this limit doesn't exist. So I'm going to use the Cauchy-Adamard formula for the radius of convergence, which was 1 over the lim sup of the nth root of the modulus of a sub n. So I simply substitute that in. I get the lim sup of 3 plus minus 1 to the n. Now that lim sup, this limit doesn't exist, but the supremum limit does. It's just 4 in the denominator, so this is a quarter. So that's my radius of convergence, and the series converges for mod z less than a quarter. One of the lovely things about power series, of course, is that you can kick them around. You can do just about whatever you like to them. As long as you stay inside the region of convergence, then nothing goes wrong. So if I've got a power series with a radius of convergence r, then as long as I'm inside this disk, the derivative of f exists, and you can just differentiate term by term. So you pull the power down the front, decrease by 1. So this term by term differentiation of power series is permissible in the region of convergence. And I've just got a little proof of that here. So if we let g of z be this formal derivative, this term by term derivative, then since we know that the limit of n to the 1 over n is 1, then g also has a radius of convergence equal to r. We simply take the nth root test on this one, on this term here, and the nth root test will give me a radius of convergence r for the an's, and then n to the 1 over n goes to 1. So if we take f sub capital N, g sub capital N, the nth partial sums of the f and g respectively, then since we've only got finite sum, then f dashed of n is g of n. And we can then write the following. We can take the f sub n of w plus h minus f sub n of w, and then divide by h. So we're looking at the derivative quotient minus this g sub n. And we can rewrite this then as 1 over h, 1 over the absolute, the modulus of h, times the integral of g sub n z minus g sub n w, where c sub h is a straight line from w to w plus h. So in the complex plane, we've got some complex number w here, and we've got w plus h, and there is our contour connecting the two. And so you can then rewrite, because this f dashed is g, we can now write this in this form, where this is the straight line, and this is all going on inside the disk of radius r. Now if we let n go to infinity, we obtain this difference here is equal to this expression here, taking limits, which is less than this supremum here. So it's the length of the contour, which is absolute value of h, so that cancels, and we just get the supremum along this curve of gz minus gw. Now since the right hand side goes to 0 as h goes to 0, we therefore have f dashed of w is equal to g of w. So all of the above results work for power series centered at z0 in a complex number. That is, we derived it here for series based at the origin, or we can just shift the origin to z0, and then the same result's going to work for this general power series here, this general Taylor series, I should say. In this case, the region of convergence then is going to be we're simply moving the origin, so it's the modulus of z minus z0 less than r. So as with the previous result, that function with a radius of convergence r has a derivative at and near z0, provided we stay inside the open disk mod z minus z0 less than r, and hence it represents an analytic function in this region. Now, you've already seen these series, so I write down here what are called known series, and the one in the sense that you should know them. So in most of what follows, we're going to find new series by manipulating the standard Maclaurin series for the basic functions. And you should learn these carefully if you don't already know them. There's the lovely series for e to the z. There's the series for sine. Sine is an odd function, so of course it's only got odd powers of z. Cos is an even function, so you only see even powers of z. The sine is easy to remember because it's very similar to the sine, except there's no alternating of sines in there. And same with the cosh. Now, all of these are entire functions, so that means they converge for any value of z. These are valid for all z. These two geometric series, 1 on 1 minus z, is this sum. And this one's only valid for mod z less than 1. And you can see what's happening here with this because the 1 on 1 minus z has a singularity at z equals 1. And so the biggest disk you can draw centered the origin that just misses the singularity is that one. And that's going to converge for mod z less than 1. This one has a singularity at minus 1. So again, the biggest open disk you can draw centered the origin in which the function's analytic is mod z less than 1. We can now integrate this second one, for example, and we get a nice series for log of 1 plus z, but again, it's only valid inside mod z is less than 1. Now, just to do a little bit of manipulation with these things, we'll find some Taylor series about other points. So I want to find the Taylor series for sine z about the point z equals pi. And then we're going to find the Taylor series for tan z about z equals 0. This one is not so, the patterns are there, but they're very complicated, as we'll see for this one. So here's the worked solution for this. We start off with f of z as sine z about z equals pi. So I need to relate sine of z back to sine of z minus pi. So if you just write equals sine z minus pi, if you expand this out, you see you're out by a minus sign. So sine of z is minus sine z minus pi. And then I can use the well-known series for sine, replacing z with z minus pi. So I have minus z minus pi minus z pi cubed on 3 factorial plus and so on, and there it is in sigma notation. And this again will be valid for all z because the function is analytic everywhere. Now tan z is a little bit more tricky, and firstly we can save ourselves quite a bit of time by noting that tan of z is an odd function, so I can write this just using odd powers of z. And moreover, the tan is defined to be the sine over the cos. And what I do now is I'm going to multiply both sides of this by cos z, and then turn sine and cos into their respective series. So I'm going to get this series we're trying to find, multiplied by cos z, but turn cos z into its series, and that should equal sine z, and put sine z in terms of its series. If you now compare the powers of z, then the coefficient of z to the 1 we're going to get from here, we'll get an a1 times z, and that's got to be 1, so immediately a1 is 1. For the sine or for the coefficient of z cubed, we'll get a z cubed from a3 z cubed times 1. We're going to get an a1 times minus 1 on 2 factorial. And we're going to get also for z cubed, we have on the other side, we have minus 1 on 6. So minus 1 on 3 factorial is going to be minus a half, because a1 was 1. Minus a half a1 plus a3, so a3 turns out to be a third when we simplify it. Similarly for a5, the coefficient on this side is 1 on 5 factorial, it's 1 on 120. We'll get an a5 from this one, multiplied by 1. We'll get an a5 from this one, a3 times minus 1 on 2 factorial, and an a5 times this one. So they're the terms we're going to get, and I've simply substituted in A3 and A1 in, and in here, and I rearrange, I make A5 the subject, so I get 2 on 15. Well, you can continue on your merry way with this and work out higher degree terms, but just to write down what we've got for the first few terms of tan of z, then is z plus a third z cubed plus 2/15 z to the fifth. Now this is going to be valid in the largest open disk in which tan of z is analytic, and tan of z has its singularities, its first singularities at plus or minus pi on 2. So the series will work inside the disk radius, open disk radius pi on 2. Now, obvious question, what are these numbers here? They look a bit suspicious and rather interesting, and I'll leave you to have a Google those, a bit more information on them. They're connected with the Bernoulli numbers. So these coefficients are given by this formula. It's 2 to the 2n times 2 to the 2n minus 1 on 2n factorial times the nth Bernoulli number. Now, there are many different versions of the Bernoulli numbers. You can have a look on the web and see which one I'm referring to here. So that's just a little entree into series. This is the Taylor series, and we're going to move from here next into the more interesting series, the Laurent series.